Fluorophores are a class of compounds with fluorescent properties that have been extensively studied due to their widespread use in fluorescence microscopy and bioluminescence experiments. According to their different structures and characteristics, fluorophores can be divided into two categories: organic fluorophores and inorganic fluorophores. Organic fluorophore is a compound composed of carbon, hydrogen, oxygen, nitrogen, and other elements, which has good solubility and processability. Common organic fluorescent groups include fluorescent dyes, fluorescent polymers, and organic small molecular fluorescent probes. Inorganic fluorophores mainly refer to fluorescent materials composed of metal ions or semiconductor materials. This type of fluorophore has excellent optical properties and stability and is commonly used in applications such as fluorescence microscopy imaging and fluorescent labeling. The most common fluorophores are organic compounds containing pi-conjugated systems and heteroatoms such as nitrogen and sulfur. Most of their molecules have a planar structure and have a certain degree of rigidity. Their photophysical properties are caused by the valence electron transition of the molecules. Common fluorophores include the following. Xanthine fluorophores mainly come in two forms, fluorescein and rhodamine. Fluorescein was first synthesized by A. von Baeyer in 1871 using resorcinol and phthalic anhydride as raw materials. Rhodamine was synthesized by Noah Litting and J. Wonsky in 1905. It is widely used in optical materials research. By modifying the structure of xanthine fluorophores, xanthine derivatives with different photophysical properties can be constructed. Coumarin, also known as naphthone, 1,2-benzopyrenone, benzophenone, etc., is widely present in nature and was discovered and named by A. Vogel from Lingling fragrant beans in 1820. The coumarin precursor itself does not exhibit fluorescence. After introducing electron-withdrawing conjugated groups at positions 3 and 4 on the coumarin ring, and electron-donating conjugated groups at positions 6 and 7, charge transfer occurs within the molecule to form a strong push-pull electron system, resulting in fluorescence. The photophysical properties of coumarin fluorescent groups can be controlled by introducing different electron-withdrawing and electron-donating groups. Bornodipyrimethane, abbreviated as BODAP, was first synthesized and reported by A. Tribes and F. H. Kreutzer in 1968. Its structure is shown in Figure 3. The molecular structure of BODAP is strong, the structure is easy to modify, and the fluorescence quantum yield is high. Commonly used modification strategies are the introduction of aryl, ethinyl, styrol and other groups into its structure, or the push-pull electron system to control its fluorescence properties. 1,8-naphthalimide has a high fluorescence quantum yield and is easy to modify. It is commonly used as a DNA embedding agent and biomarker. Its chemical structure is shown in Figure 4, with a large conjugated system. One end of the molecular structure is a strong electron-withdrawing group called an imide, while the other end is usually modified with an electron-donating group to form an intramolecular charge transfer system, exhibiting good fluorescence performance. Pyrene is a polycyclic aromatic substance, first discovered by Aileron in 1837 in the residue of distilled coal tar. Pyrene is prone to form high quantum yield and long-lived X-imer complexes in solution. The optical properties of these X-imer complexes are extremely sensitive to their microenvironment and are widely used in environmental parameters such as pH and temperature, as well as for the labeling and detection of small molecules, proteins, and nucleic acids. Cyanine is typically composed of two nitrogen atom centers, one of which is positively charged and linked to a conjugated chain, and the other end of the conjugated chain is linked to another nitrogen center to form a charge transfer channel. This distinctive structural feature is often referred to as the push-pull alkene. By changing the length of the methotrexate carbon chain in the middle region, its fluorescence properties can be adjusted within a wide wavelength range, and it has wide applications in nonlinear optical materials, solar cells, and other fields. Phthalocyanine was discovered by the German chemist A. Braun and others in 1907. Its structure consists of 8 nitrogen atoms connected to 4 isoindole rings, and has a highly delocalized 18-pi electron macrocyclic conjugated system. The central hole of phthalocyanine can be coordinated with more than 70 kinds of metals, and the choice of central metal determines the physical and chemical properties of its complex. Phthalocyanine compounds and their metal complexes have strong absorption in the infrared/near-infrared region and are widely used in nonlinear optical materials, tumor photodynamic therapy, and other fields. Effect of conjugated system on fluorescence. Generally, Increasing the length of the p-electronic conjugation system can improve the fluorescence efficiency and redshift the fluorescence. The existence of steric hindrance effect can destroy the coplanarity and conjugation degree of molecules, thereby weakening the fluorescence. Stereoisomerism also affects fluorescence intensity. For example, trans-stilbene is strongly fluorescent, while cis-stilbene has no fluorescence properties due to the steric hindrance effect. Effect of substituents on fluorescence. Most organic fluorescent substance molecules contain aromatic rings. The introduction of substituents on the aromatic rings can change the photon yield and emission wavelength of fluorescence. Usually, ortho and para positioning groups can enhance fluorescence, meta positioning groups can weaken fluorescence, and nitro and azo groups can prevent the generation of fluorescence. The introduction of electron donating and electron withdrawing groups at both ends of the molecule can cause the dye to redshift and be accompanied by an enhancement of fluorescence. The presence of halogen atoms is detrimental to fluorescence. The introduction of amino groups can enhance fluorescence. Effect of molecular ring structure on fluorescence. The closed loop of the dye molecules is very beneficial for the generation of fluorescence, which can increase the coplanarity and rigidity of the molecules and enhance the fluorescence. Many compounds that are non-fluorescent or a very weak fluorescence are chelated with metals to produce chelates with a cyclic structure that display strong fluorescence. The molecule contains hydroxyl groups and can form intramolecular hydrogen bonds, which in most cases can increase the fluorescence intensity. Fluorophores are widely used in cell staining, biomedical imaging, fluorescence positioning, optical nanomaterials, tumor treatment, and other fields.